All right, let's get this show on the road. It is 2019, and we are going to finish this gosh darn paper. So this is the third part of Attention is All You Need. And I see it on Twitch, and there's YouTube. Okay, excellent. The third part of Attention is All You Need. So we have already spent 2 hours reading this, 10-page paper? Yes, this 9-page paper, and we are going to hopefully wrap it up today. And if we have extra time at the end, I don't know if we're going to. I think once we get to the results, we'll have pretty fast going, because it's just going to be like, we tried it and it did good. We might spend some time working on optimization, on implementation. We'll see. We'll see how we're feeling then. And I'm also just coming off of the second 4-day weekend I've had in a row, which was lovely. But it's also going to take some time to get my brain in gear. Okay, where were we previously? I think we ended up in section 3.2.3. But let's quickly do some recapping of what we did in the first 2 sessions, just so we're all on the same page. And if you are watching these later, I mean, you can just skip ahead until we get to the point where it's new. So the general idea is that Attention is All You Need introduces a new model architecture, transformers, that do not involve recurrence or convolution. So they have the benefit over recurrent models, which are still being used for many of the same applications that transformers are used for, that you can train all time steps simultaneously. You don't have to train time step n-1 before time step n. So you can train them much more quickly, and they are more parallelizable. So there's perhaps not a, cognitive reason to do it like this, but there is a practical reason in terms of implementation of why to use this particular model architecture. And the architecture looks like this. So we're using embedding. So these are words, and I believe they're doing machine translation as well. So these would be the input would be embeddings for the word in the input sequence, and then the output would be probabilities for words in the target language. So if we were going from like English to Turkish, this would be English, this would be Turkish out. The embeddings are just like embeddings in a different model. We've got a course on Kaggle around embeddings, so if you're not familiar with them, you can check that out. The positional encoding we learned about last time, and actually visual transformer, illustrated transformer, sorry, is the blog post we've been using. And that looks like, scroll, this. So each position, 0 through n, is assigned a specific function that is a concatenation of a cosine and sine, I believe. Inari on Twitch says, "Hi, you're back. Happy New Year." I am back. Happy New Year to you as well. So these can continue indefinitely, and sort of this pattern will repeat. And this is how you get things like the first word is before the second word, rather. And you could use just like an integer, but they are using this instead. And I think last time we came down on, we couldn't quite figure out why they'd done this instead. Besides the fact that you were always going to have an array of the same width. So you can have a number that is greater than 510, or, you're not constrained as much by that. And also there's a bit of a smoothing. So things that are closer to 1 are going to look more like 1, and things that are farther away from 1 are going to look less like 1. So that's the positional encoding, and the output is the input 1 to the right. So we have the current word, and then we have the word before it. MultiHead Attention is this dude right here, and basically you are doing multiple inputs at the same time. So the values, the keys, and the queries, these are all I think these are arrays and not matrices, or sorry, these are vectors and not matrices. And these are all trained for each time step. And then you take these, so these are, oh, actually, I think these are tensors, this is a vector, and then this is a scalar. So you train multiple ones at once, and then you sort of squeeze them down into a single number, and that's multi-headed attention. And then this little bypass here means that you're also sort of averaging over the input. So it's sort of a, not quite regularization. What would you call that? It sort of tamps down the process. Oh wow, words are really hard. So you can't just go completely off the rails on this one, and this will, help to make sure that you are being more faithful to your input. Jance says, Happy New Year to Dr. Tapman and all the Kagglers here. Excited to join in. We're excited to have you. Welcome. And then we've got a feed-forward network, which we haven't read about yet, and then the same sort of additive and normalization step. And then the output embedding, you have masked multi-head attention, and the masked just means that you don't attend to things in the future. So you don't, you don't say what the next word is by looking at the next word, because that's the best way to solve that problem, but clearly is not going to work if you're doing online translation. Online meaning as the event is happening, not using the internet. And then you take that output and the previous word, do multi-headed attention over that, continue your addition and normalization step, feed-forward network, which again we haven't quite talked about yet, this addition and normalization step, and then you take your, I think at this point it is a tensor of n by x dimensions, transform that into a linear output, and then take the softmax across the probabilities in your output vocabulary, and then you get the translation out. Just like that. Very simple, very few moving parts, completely easy to understand. It's none of those things. So that's sort of the general idea of what we've been doing so far. And hopefully we're more or less on the same page now. And it took us a good 2 hours to get to that point. So don't worry if you are just joining and that was all gobbledygook to you. I'm gonna take a little sip of water, gotta stay hydrated. Okay. Oh, right. And so this is, I don't think it actually says it. I think this is the encoder and this is the decoder. So this half is the encoder with the input embeddings, and this half with the output embeddings is the decoder. Ben Shadar says, Happy New Year. Happy New Year to you as well. Okay. And what else we were talking about? Let's start over with 3.2.3 because I don't remember it very well. So the transformer uses multi-head attention in 3 different ways. So multi-head attention is this, where we train multiple value, key, and query tensors, no matrices at the same time. In the encoder-decoder attention layers, the queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. Oh, yeah, I remember this. So we use the key and the value, and let's see, there was a really good illustration of this in here. Somewhere in here. Nope, that's too far up. Well, anyway, in here somewhere, there's a really good illustration of this, and I don't see it right away. So we use some of the trained things from the previous decoder layer, and then one of them from the encoder. So that happens at this step, and that's why of the 3 arrows that go in, 1 comes from here and 2 come from here. So that's sort of how you transfer knowledge, quote unquote, between the encoder and the decoder. And this allows every position in the decoder to attend over all positions in the input sequence. This mimics the typical encoder-decoder attention mechanisms in sequence-to-sequence models, such as citing some models. And then the encoder contains self-attention layers. In a self-attention layer, all of the keys, values, and queries come from the same place. In this case, the output of the previous layer in the encoder. Each position in the encoder can attend to all positions in the previous layer of the encoder, which I think they mentioned is useful for things like long-term agreement, where something very early in a sentence or a text needs to you need to know about something early in a sentence or a text in order to figure out what something should be later. So for things like grammatical gender, if you have a word that is gender inflected and refers to a much earlier word, then you need to know what the gender of the earlier word is in order to get that correct. Yes, so we've finished this bullet point, and then the third bullet point says, similarly, self-attention layers in the decoder allow each position in the decoder to attend to all positions in the decoder up to and including that position. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. So basically, if you're reading along right to left, you can't look to the left of where you are currently to figure out what's happening right now. We implement this instead of a scaled dot product attention by masking out, setting to -infinity, all values in the input of the softmax, which correspond to illegal connections. All right. Oh, we've read all this because we've read all the way to positional encoding. Yeah. Okay, I'm remembering this now. Right, so the positional encoding is this thing that, as I remember, we were a little bit confused about, but like it makes sense to me what they're doing. I'm not entirely sure why they're doing it that way, but it seems very fancy, so maybe that's why. So they also experimented with using learned positional embeddings. So instead of sort of creating these embedding arrays, but position encoding arrays, they learned them, and they found that the tube versions produced nearly identical results. So you would want to generate those rather than learning them because the outputs are the same, and it takes more time to learn something than it does to, just create it from rules. And we chose the sinusoidal version because it may allow the model to extrapolate to sequence lengths longer than the ones encountered during training. So I guess the intuition there is because it is, you can predict what, so this only goes through 19, sorry, this has 20 items in it, 0 through 19. We can predict what 20 is going to look like based on the existing pattern, and I think they're suggesting that the model might be able to do that extrapolation as well. Did we talk about, yeah, and we talked about self-attention as well, and I think we ended on this paragraph. I should have gone back and watched the last video, but I usually do that on Tuesdays, and I was on vacation on Tuesday. In this section, we compare various aspects of self-attention layers to the recurrent and convolutional layers commonly used for mapping one variable length sequence of symbol representations to another sequence of equal length with x sub I, z sub I in the set of things with the dimension d, I think, such as a hidden layer in a typical sequence transduction encoder or decoder. So why are we doing the thing that we have just proposed instead of using convolutions or recurrent models like long short-term memory? Specifically bidirectional long short-term memory with attention was and continues to be for many tasks state of the art when this paper came out. Oh, thank you. Inari says the R is real valued. Helpful. Thank you. Just means these are encodings, e.g. word to vec. Oh, I see. Okay. So you know all of the possible things that it could be. So they're both drawn from the same set, if that makes sense. Sorry, if that's correct. That's what makes sense to me. Whether or not that's the right thing. Okay. Okay, so they use self-attention for 3 reasons. There's 3 things that they want, desire out of. And here he says, yes, thank you, very helpful. Oh, and Bubble Ride also said the R to the D power is just a vector of D elements that are float. Okay, helpful, thank you guys. I spent a lot more time learning linguistic notation than mathematical notation in graduate school, and I think it shows a little bit. All right, so the 3 things that they're doing are, 1, they're looking at total computational complexity per layer. They're also looking at the amount of computation that can be parallelized as measured by the minimum number of sequential operations required. And then the 3rd, which they bring up in a second paragraph, I don't know, these paragraphs are, the organization of the paragraphs is a little confusing to me. The 3rd is the path length between long-range dependencies in the network. Bubble Ride says transduction encoder. What is transduction? I think when they say sequence transduction, they just mean sequence to sequence. But we can check that out, actually. Sequence transduction. Oh, that's not spelled well. Don't show again. Thank you. The transformation or transduction of input sequences into output sequences. Yeah, it's literally just sequence to sequence. I don't know why they're saying transduction. It's probably a disciplinary thing that's more machine learning-y than natural language processing-y. All right, 3rd is path length between long-range dependencies in network. Learning long-range dependencies is a key challenge in many sequence transduction tasks. One key factor affecting the ability to learn such dependencies is the length of the paths forward and backward signals have to move through in the network. The shorter these paths between any combination of positions in the input and output sequences, the easier it is to learn long-range dependencies. That makes sense to me in a machine learning context. I don't know that that is correct for human brain, but this is not a human brain paper. Hence, we also compare the maximum path length between any 2 input and output positions in networks composed of different layer types. As noted in Table 1, a self-attention layer connects all positions with a constant number of sequentially executed operations, not observations, whereas a recurrent layer requires O(n) sequential operations. So self-attention, there is, if we continue adding different operations, that doesn't change the number of things that we have to move through to get to each one. Whereas if we're doing recurrent, I can zoom in a little bit so it's a little bit bigger. Every time we add a item to our sequence, we have to also add it to our operation to get to an earlier item, which, yeah, we'll just continue on. In terms of computational complexity, self-attention layers are faster than recurrent layers when the sequence length n is smaller than the representation dimensionality d, which is most often the case with sentence representations used by state-of-the-art models in machine translation, such as word piece and byte pair representations. So as long as your sequence is smaller than your total vocabulary, self-attention layers are faster. And we talked about byte pair, and that's where you replace unique differences between two strings with a little. We definitely read this earlier, but it's good. It's been a week, and my brain does not remember all of this. You replace it with a shorter, unique string. So like if your strings were 1, 2, 3 and 1, 2, 5, you might replace 1 and 2 in both of those with 4. So you'd get 4, 3 and 4, 5. To improve computational performance for tasks involving very long sequences, self-attention can be restricted to considering only a neighborhood of size R in the input sequence centered around the respective output position. Oh, Inri says, I think D is word length, not vocabulary, where word is tokenized word, e.g. byte pair encoded. Sorry, I'm thinking, is what that pause is. So the sequence length is smaller than the, so the size of the encoding? Oh, Inri says, no, never mind, that's wrong. Aman on YouTube says, representation dimensionality need not necessarily be the size of the vocabulary, correct? It could be arbitrary, I believe. Yeah, I think this could probably, the representation dimensionality. So it could be the dimensions of the embedding. That makes sense to me. Is that right? Good question. So it could be if you are not doing embedding and you are just doing a co-occurrence matrix for your vocabulary, then D would be the size of the vocabulary. If you're doing a lower dimensional projection, then D would be the size of the projection. Makes sense. Okay, yeah. I think that seems right to me, and if someone else is like, that's not right, feel free to just holler. Blah, blah, blah. Okay, so to improve computational performance, if you've got a really long sequence, so a sequence that's longer than your embedding dimensions, you can use a sliding window of neighborhood size R centered around the respective output position. So if your dimension is, dimensions of your embeddings are 500 and you're looking at like a novel, you might look at 249 words on each side of your target word and then move that sort of window that you're looking at along as you go. This would increase the maximum path length to O of n divided by R. So I believe n was the sequence length, correct? The sequence length divided by the size of the sliding window. So it is no longer constant, but it is smaller than O of n. JRC Fernandez says, what is the topic today? We are continuing to read Attention is All You Need from NeurIPS 2017. Inri says, embedding dimensionally is usually around 200, which is definitely bigger than the typical sentence length. Yeah, true. But if you're doing longer text, so for example, summarization, often you will have a, I'm using my hands here, you'll have a much longer sequence than your typical embeddings. Also, I had to approve that comment because Twitch thought that it was inappropriate because it had NLP in it for some reason. Shrug. Okay. Right, so we can use a sliding scale, a sliding window instead of looking at everything if we have a very long input text, but they didn't actually do it. They are going to look at that in future work, which they've probably already done because this was from a bit ago. Okay, so a single convolutional layer with kernel width k is less than n does not connect all pairs of input and output positions. Doing so requires a stack of O n divided by k convolutional layers in the case of contiguous kernels, or O log of k n in the case of dilated convolutions. Oh, I don't know what those are. Bubble Ride says, what's wrong about NLP? People are probably using L to represent I. That was on Twitch. Increasing the length of the longest path between any two positions in the network. Convolutional layers are generally more expensive than recurrent layers by a factor of k. Separable convolutions, however, decrease the complexity to the dot product of k n d plus n and d squared. Even with k equals n, however, the complexity of a separable convolution is equal to the combination of a self-attention layer and a pointwise feed-forward layer, the approach we take in our model. So convolutions would be just as good in terms of the path length between points as what they're doing, but they're more expensive to train, is what they're saying here, I think. As a side benefit, self-attention could yield more interpretable models. We inspect attention distributions from our model and present and discuss examples in the appendix. Not only do individual attention heads clearly learn to perform different tasks, many appear to exhibit behavior related to the syntactic and semantic structures of the sentence. Okay, so the reason that we're not using recurrent structures, the reason that they're proposing that this is better than recurrent structures is that recurrent structures are, in order to get from one point to another, you have to do many more operations. In convolutional neural networks, you don't necessarily have to do more operations to get from one point to another in the best case scenario, but they're more expensive to train, and the model that they're proposing is more easily interpreted than convolutional networks. Okay, so this is their argumentation about why their model is good and their paper should be published, and clearly it was published. Okay, training. I'm thinking this will probably go pretty fast. Training data and batching. We trained on the standard WMT 2014 English-German dataset consisting of 4.5 million sentence pairs. This is a very standard machine translation dataset. Sentences were encoded using byte pair encoding, which has a shared source target vocabulary of about 37,000 tokens. For English-French, we used a significantly larger WMT 2014 English-French dataset consisting of 36 million sentences, and split tokens into 32,000 word-piece vocabulary. Sentence pairs were batched together by approximate sequence length. Each training batch contains a set of sentence pairs, approximately 25,000 source tokens, and 25,000 target tokens. Set of sentence pairs batched together by approximate sequence length. Why did they do this? I'm confused about why they did this. This might have just been something that they did to make the model easier to code? Question mark? I don't know, maybe they'll talk about it. Hardware and schedule. Well, so because their model, so the reason I'm hung up on this is because their model should be able to handle sequences regardless of length, because maybe they're hard coding length into it and they're doing padding. Henry says probably more efficient. Yeah, that makes sense. So I don't think there's like a I think that this is an engineering choice and not a sequence choice, and not a science choice. All right. We trained our model on one machine with 8 NVIDIA P100 GPUs. That's a fair amount of compute. Finger draw says, is steps similar to epochs? I'm looking for where we were talking about 6. Amon says, I think the batch size will be the function of the GPU memory available to them. That makes sense. Sorry, steps. That's also not how you spell steps. There we go. Oh, I haven't gotten there yet. For our base model using the hyperparameters described throughout the paper, each training step took about 0.4 seconds. We trained the base model for a total of 100,000 steps, or 12 hours. For our big models, described in the bottom line of table 3, step time was 1 second. The big models were trained for 30,000 steps, 3.5 days. Bubble Ride says 12 hours. This is like 2 weeks 10 years ago. Yeah, I know. Things are getting so much faster. And Fingerdraw says, is steps similar to epochs? I don't know. Aman says, steps is one mini batch. Epoch will be a complete roundup of the whole data. Oh, yes. Okay, that makes sense. I don't know why they wouldn't say mini batches then. Question mark. Optimizer. We used the Atom Optimizer citation with beta 1 0.9, beta 2 0.98, and this funky E 10 to the negative 9th. We varied the learning rate over the course of training according to the formula. Learning rate equals dimensions of the model to the negative 1/2 power times the dot product of the minimum of the step number to the negative 1/2 power and the step number times, with the dot product of the warm-up steps to the negative 1.5 the power. Inri says the funky E is epsilon. Thank you. Polaris says steps is regularly used as a term. Good to know. Thank you. And Ryan says, I figured they were just streaming in the data while they were training, so it is not necessarily similar to epochs because epochs would be a loop through the whole training set. Okay, so this is sort of like stepping through the data, I guess. So learning rate, this corresponds to increasing the learning rate linearly for the first warm-up steps, training steps, so burn-in, and decreasing it thereafter proportionally to the inverse square root of the step number. So taking smaller steps as you go. We used warm-up steps set to 4,000. Inri says, also note that beta 2 equals 0.98 because the default is 0.999 and usually left alone for 99% of the cases. Wonder why 0.98? That's a great question. I have no idea. Yeah. I don't know, maybe they tried 0.99 and it didn't work? Because they were, wait. So there was, they were doing something, I remember vaguely, that meant that the learning rate was a little bit slower. Do you remember that? Am I making that up? There was definitely something where we took, yeah. So they took the square root of the dimensions and they divided it by that to, as a scaling factor. So maybe it was to account for that. Ryan says, I doubt that it really makes much difference. Yeah, I don't know. It might be one of those things where, like, if you're chasing state of the art, it matters more, but if you're just, like, doing it for real, it matters less. All of these are empirical questions. So that's the optimizer. Regularization. We employed 3 types of regularization during training. Residual dropout. We applied dropout, citation, to the output of each sublayer before it is added to the sublayer input and normalized. In addition, we applied dropout to the sums of the embeddings and the positional encoding in both the encoder and decoder stacks. For the base model, we used a rate of pdrop equals 0.1. So that is happening, scroll, right here. They're doing dropout, and then also the second place where they said that they were doing it that I have forgotten about already. Bubble Ride says, optimization is a dark art, like alchemy. It is, yeah. Like, presumably alchemists knew some things about chemistry, but there are also some things where they were like, I don't know, it just worked. Which I feel like is where machine learning is as a field right now, which is kind of frustrating to me personally. And then they also use label smoothing. So during training, we employed label smoothing value of epsilon, thank you, sub ls equaled 0.1. This hurts perplexity as the model learns to be more unsure, but improves accuracy and blue score. So this is literally just to make the metrics that they're targeting better. And the second place they did it was to the output of each sublayer. Okay, so there's also dropout. So there's dropout once after you do the embeddings, and then again each time you finish your sublayer bit. So here are their results. Inri says, fun fact, there was a NeurIPS test of time talk last year called Alchemy. That sounds very reasonable. The transformer achieves better than blue scores than previous state-of-the-art models on English to German and English to French News Test 2014 tests as a fraction of the training cost. So we have some other examples. We have ByteNet, Deep Attention plus POSANK, Positional Unknown. I don't know what that is. GNMT plus RL, Conv S2S. So this is one that I've heard of, convolutional sequence to sequence. Deep Attention and POSANK, question mark, ensemble, GNMT and RL ensemble, Conv S2S ensemble, and with blue, bigger is better. So Transformer, their big models did really well. Oh, if you train longer, it gets better. Although, interestingly, their base model, which is the one that they propose here, does not do as good. So the English to Dutch does better, just the base model, but the English to French does worse than these other models, which is interesting because English and German, my apologies. English and German are much more closely related than English and French. So yeah, I don't know if that would have an effect here or not. I haven't done that much work on machine translation. Bubble Ride says, does Kaggle provide 8 GPUs as well? I mean, I guess if we provide 1 GPU at a time, you can have multiple sessions running at the same time, and I don't know the exact number of those sessions, but I don't think it is necessarily 8. I hope that answers your question. Inri says there's a lot more data for English French. True. So it could be that the attention model, you know, has performs better with sparse data. Shrug. But in terms of training cost, I mean, the model proposed here really does much better than pretty much any of the other models that they compare it to. So, and you know, training cost is an important thing to consider. It costs money, it costs time, there's, you know, environmental impacts of spending more time training your model and burning whatever type of fuel you're burning to do that. So they have a not quite as performant, still pretty good model that they've discussed in detail here, and then they have a larger model that does better because you have to beat state of the art to get into NeurIPS. All right, and then results. Oh, let me get rid of this little search bar, sorry. Machine translation. On the WMT 2014 English to German translation task, the big transformer model outperforms the previously reported models, including ensembles, by more than 2.0 blue, establishing a new state-of-the-art blue score of 28.4. As an aside, I don't want to get into blue too much because I am working on a blog post about it, and I will put all my opinions in there. The configuration of this model is listed in the bottom table of Table 3. The bottom line of Table 3. Training took 3.5 days on 8 P100 GPUs. Even our base model surpasses all previously published models and ensembles at a fraction of the training cost of any of the competitive models. On the WMT 2014 English to French translation task, our big model achieved blue score of 41.0, outperforming all of the previously published single models at less than a fourth of the training cost of the previous state-of-the-art model. The transformer big model trained for English to French used dropout rate p equals 0.1 instead of 0.3. Why? Question mark. Presumably just because it worked better and they tried it and it worked good, and so they're doing that instead. For the base model, we used a single model obtained by averaging the last 5 checkpoints, which were written at 10-minute intervals. For the big models, we averaged the last 20 checkpoints. We used a beam search with a beam size of 4 and a length penalty alpha equals 0.6. These hyperparameters were chosen after experimentation on the development set. So again, they literally just tried a bunch of stuff and then figured out what worked good. We set the maximum output length during inference to input length plus 50, but terminate early when possible. So that's probably going to improve the time it takes to do inference. Bubble ride, summary, we won. Yeah, pretty much. Table 2 summarizes our results and compares our translation quality, questionable, and training costs to other model architectures from the literature. We estimate the number of floating point operations used to train a model by multiplying the training time, the number of GPUs used, and an estimate of the sustained single precision floating point capacity of each GPU. So this is just a measure of how many transformations did you have to do to train your thing. So the reason I said questionable about translation quality is because of, not that I'm dunking on their model, but that I have problems with blue as a metric, which, again, I'm gonna chuck that in the blog post and save that for later. Atrof says, Happy New Year, Kaggle. Happy New Year. Model variations. To evaluate the importance of different components of the transformer, we varied our base model in different ways, measuring the change in performance on English to German translation on the development set, News Test 2013. We used a beam search as described in the previous section, but no checkpoint averaging. Why? Why did you not do checkpoint averaging here? We present these results in Table 3. In Table 3 rows A, we vary the number of attention heads and the attention key and value dimensions, keeping the amount of computation constant as described in section 3.2.2. While single head attention is 0.9 blue worse than the best setting, quality also drops off with too many heads. Ugh, so this is a Goldilocks thing. Ryan says, blue is pretty interesting. Had always just skimmed it in the results, but didn't know what it was. Finally learned about it in Andrew Ng's course. Yeah, it is interesting. I might have said this on the stream before, but right now I think the most interesting and hardest problem in NLP is sequence-to-sequence metrics. And I like human in the loop. That is my stance on the question. Inri says, what would you use instead of blue? I mean, there's rouge, which is not necessarily better, but I mean humans. Like asking humans, like, again, human in the loop, that's what I like. But it's expensive, it takes forever, I understand why you might not do it, but I really think that should be what our gold standard is. But also, I clearly believe in the importance of humans and language use because I spent a long time getting a degree in that. All right, Table 3. Ooh, let's zoom out a little bit so we can see the whole thing. Just a tiny bit more. Can I get it all? Yes, I can just get it all in one. Variations on the transformer architecture. Unlisted values are identical to those of the base model. All metrics are on the English to German translation development set News Test 2013. Listed perplexities are per word piece according to our byte pair encoding and should not be compared to per word perplexities. Okay, that's good to know. Because perplexity will often be reported on per word, so what they're saying is don't take this table and compare it to other tables. Mine says Andrew has good visualizations you might want to borrow. Yeah, it's good to know. I'll look into them. All right, so they varied n, which is the number of something, the dimensions of the model, the dimensions of the feed-forward neural network. H is the number of heads that you do at the same time for multi-headed attention. dk is the dimension of the key tensors, or matrices, sorry. D is the dimension of the value matrices, dropout rate, epsilon ls. Oh, we just looked at that. What is that? Also, what is n? Oh, label smoothing. And then number of training steps. And then these are the output. So this is the perplexity on the byte pair encoding. This is blue, which is sort of the score. Higher is better. And the parameters is the number of parameters that they trained, I'm assuming. Inri says n equals beam search depth. Oh, you know what? That looks right, because when they talked about beam search, was right in here. Big models. No, because their base model had a default of 4, and here it is 6. So it's not that. What is n? This is a mystery. Inri says parameter equals number of trainable neural network weights. Yeah, thank you. Where is 6 coming from? 6. Nope. Oh, it's the size of the layers in the encoder. Okay, that makes sense. So it's how deep the network is. All right, so it looks like, oh, sorry. So, and for perplexity, lower is better. So the big model, no surprise, did really well. This is when they trained the positional embedding instead of using, I left that tab, but the sort of like up and down thing. Bubble Ride says, I guess early stopping does not make much sense here. Is it common to just predetermine the number of steps? I don't know. I'm not super familiar with steps, which you may have gotten the impression of from earlier when I was like, I don't know what steps are. Yeah, if anyone knows whether it's common to predetermine the number of steps instead of sort of like doing early stopping. Oh, Ryan actually has just chimed in. When you're dealing with larger data, yeah, it's more a function of how much compute time you have. That makes sense. This is a paper from Google, so I'm imagining they had a fair amount of compute time. Although they are trying to be like more efficient here, so that's nice. So it looks like, no surprise, fewer layers is less good, so deeper tends to be better. So when they increase the depth to 8, they get a little bit of a downward movement in perplexity, which is good, and upward movement in blue, which is good, but obviously have more parameters to change. Making the model bigger improves performance. That's not super surprising, or sorry, increasing the number of dimensions. Increasing the dimensions of the feed-forward neural network also improves performance. H is the number of heads, and this is the sort of Goldilocks zone that they mentioned earlier. So it looks like 16-ish is better than 32 or 4 for reasons unknown. Inri says, maybe they do early stopping unless list steps is a reference. Yeah, I don't know. I don't think they've mentioned it. So that is the number of heads. So they've used 16, which is the best given their experimentation for their big model. The dimension of the keys and the values, and these dimensions need to change together because you're using one to reference the other. And this looks like, oh, I see. So as the number of heads increases, they're decreasing the dimensions of the keys and the values to keep the total number of computations the same. So that's what they mentioned. But if you just decrease the number of dimensions in the keys, then your performance goes down. So bigger those matrices they're training as part of the attention, bigger is better. So it would be interesting. I know why they decreased the dimension in addition to increasing the number of heads, but it would be interesting to see what just increasing the number of heads and keeping the dimensions constant would do. And it looks like they didn't do that. Yeah, no, they didn't just change the number of heads. Bigger model is better. I think we said that. Bigger feed forward is better. For dropout rate, again, it looks like a little bit of a Goldilocks zone. So 0 is less good, but 0.2 is also less good. And then for the smoothing, that's also... Oh, no, actually, it looks like a higher smoothing rate. No, it's not. I was going to say a higher smoothing rate is better. It increases blue, but it lowers perplexity, which I think they mentioned in the text as well. Inri says, as a stats major, it really annoys me when 95% confidence interval isn't listed. Who knows? Maybe all of these metrics are statistically equal. Yeah, we have no idea what the variance is here. And we don't know if they ran multiple experiments or for each. Yeah, and Inri continues, or rather, difference is not statistically significant. Yeah, definitely. I did at one point an analysis of the statistical methods that were used across different fields of linguistics. And in general, linguists tend to be pretty statistically sophisticated, except for the natural language processing papers, where the majority of statistical significance testing was done using t-tests. Not that there's anything wrong with t-tests, but... in sort of the range of statistical significance testing available to us, it is not the fanciest tool, shall we say. Okay, so that's interesting. So this is probably the most useful table if you were putting together a model, keeping in mind that these values are for a specific task, so it's not necessarily going to transfer, and things like the number of heads may be very dependent on your specific data set, or not. Who knows? Not me. In table 3, we observe that reducing the attention key size, DK, hurts model quality. This suggests that determining compatibility is not easy, and that a more sophisticated compatibility function than dot product may be beneficial. We further observe in rows C and D that, as expected, bigger models are better, no surprise there, and dropout is very helpful in avoiding overfitting. In row E, we replace our sinusoidal positional encoding with learned positional encoding and observe nearly identical results to our base model. Conclusion. Oh, we're almost there, y'all. In this work, we presented the transformer, the first sequence transduction model based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architectures with multi-headed self-attention. For translation tasks, the transformer can be trained significantly faster than architectures based on recurrent or convolutional layers. Although it doesn't seem to involve moving between points in the input and the output, it doesn't necessarily involve fewer computations than a convolutional network. It does involve fewer computations than a recurrent network. On both WMT 2014 English to German and WMT 2014 English to French translation tasks, we achieve a new state of the art. In the former task, our best model outperforms even all previously reported ensembles. Yay, we did good. We are excited about the future of attention-based models and plan to apply them to other tasks. To my knowledge, transformers are mostly still used for machine translation. If y'all have good examples of other applications, I'd be interested in them. But they don't seem to have just sort of like immediately taken over dominance in sequence to sequence in general. We plan to extend the transformer to problems involving input and output modalities other than text, and to investigate local restricted attention mechanisms to efficiently handle large inputs and outputs, such as images, audio, and video. Making generation less sequential is another research goal of ours. Oh, that's interesting. So something like sequence to sequence, and you have your input sequence, and then during inference with your model, you might get something like the most important words out first. Is sort of what I'm getting out of there, so that would be interesting. Inri says, I think outside of machine translation, people still use seek to seek. Yeah, that's my general impression as well. The code we use to train and evaluate our models is available at https://github.com/tensorflow/tensor2tensor. Acknowledgements. We are grateful to Nell Katchbrenner and Stephen Gauss for their fruitful comments, corrections, and inspirations. It's weird to call that fruitful. And they mention appendices, but they're not there. Bubble Ride says, what's wrong about seek to seek? Nothing? So I think of seek to seek as a task, a family of tasks that is taking in a sequence and putting out a sequence. And I think sequence transduction is the same thing. Let's find out. Sequence transduction. Aman says, have a look at OpenAI, GPT, and Google BERT, excuse me, application of transformer in other areas such as classification and regression. Grounded sequence-to-sequence transduction, sequence-to-sequence encoder-decoder, because they are still using in this model an encoder and a decoder, so it's not a complete departure. RNN are considered core of seek-to-seek with attention. That's from 2017. Oh, Inri says seek-to-seek is a model as well. And there's a link. Let me grab that. I see. So it is a type of task and also the name of a model, which is LSTM. When is this from? 2014. Okay, so people say seek to mean, I'd assume, something like bidirectional LSTM with attention. That's really confusing. Okay, but that now I understand why they're saying sequence transduction rather than sequence to sequence, which I would consider, which is how I would refer to that range of tasks. And it is because they don't want to confuse people about what the models are. And here he says bidirectional LSTMs. Yep. Okay, interesting. That's good to know. And we have about 5 minutes, and I want to learn about steps. Let's see, steps. Training networks. Nope, that's not going to be enough information. How about training neural networks? Because I think this is not 2017. I think this is just going to be like the number of steps. Yeah, like walking you through the steps of training it. Change of loss between 2 steps. This might be helpful. Okay, so this is by Neural Designer. The loss function is in general a nonlinear function of the parameters. Okay, as a consequence, it is not possible to find closed training algorithms for the minima. Instead, we consider a search through the parameter space consisting of a succession of steps. At each step, the loss will decrease by adjusting the neural network parameters. Oh, okay, that makes sense. Ryan says, I think they just mean taking a step after computing the gradient. In Keras, this would be like steps per epoch argument. That makes sense. Okay. Yes, I have definitely heard this term, and I did know what it meant, and I just didn't brain it good. And then Ryan has a link. Let me pull that up for us. So this would be from Fit Generator in character, trains the model on data generated batch by batch by a Python generator. Okay, yeah, that makes sense. Okay, so this is just how long they trained it for. Got it. Henry says, I think the difference between transformers and sequence-to-sequence boils down to whether you use the self-attention mechanism or recurrent nets like LSTM. Yeah, I think I would agree. Yeah, so there's no recurrence, there's no convolution, there's no sort of either of those things. Henry says, recurrent nets are very inefficient on GPUs, so there's much benefit in getting rid of them. Yes, but there is also potentially benefit in keeping them. So there is a paper from, I think, EMNLP. There we go. That I gave a summary of relatively recently. So where is a link to the paper? But they compared the ability of recurrent networks and transformer networks on a variety of hierarchical tasks. Oh, here's the link to the paper. And they found that if you do not, so they called it a fully attentional network, quote unquote. If you do not include some sort of recurrence, you have a less good performance on tasks that require modeling a hierarchical relationship between things. So in particular, they were looking at subject-verb agreement. So something like the candles are in the cupboard versus the candle is in the cupboard, and looking at candle versus candles to figure out what the verb should be. Henry says, can you link the paper? I sure can. And I also have on my website, rctatman.com, under talks, I think, I have slides walking through this paper. And Ryan also says, if you use CUDNNGRU or CUDNNLSTM, they're very fast. Let's see. So I'm just getting the link to post in a different computer. And that is on the YouTube, and then here it is in the other one, the Twitch. And Ryan has also, I think that might actually just given us a link, and it is the link to the paper I was just talking about. Yeah, so I'm not actually familiar. I haven't played around with CUDA a whole lot, which I'm assuming is what this is. So these are the things that Ryan, nope, that's not it. These are the things that Ryan Chesler mentioned, copy, on Twitch. CUDNNLSTM as improving the, that is a good question that I do want the answer to. Improving the speed of RNNs in Keras. And CUDNN LSTM. A fast LSTM implementation backend by CUDNN can only be run on GPU with a TensorFlow backend. And it relies on CUDA and the NVIDIA drivers and CUDNN. CUDN? I don't know. How do you say that? And Ryan says, it's just the GPU optimized version, so you have slightly less flexibility in parameters, but it's way faster. Yeah, that makes sense. The one thing I do know about CUDA is that it can be hard to do replicability because some of the computations are non-deterministic by nature. Yeah, so if you're interested in doing RNNs, which perhaps you might want to do if you are interested in capturing some sort of hierarchical structure, then CUDNN LSTM might be a good option for you in Keras. All right, so it is after 10, and I do have other work to do today. We're done with Attention is All You Need. Yay! Hopefully this was helpful for everybody. I definitely feel like after reading this paper and with your guys' help, I have a much better idea of what's going on here. Ryan says, we're running into the problem on the core challenge right now, non-determinism. Yeah, it's a problem. And Bubble Ride says, thanks for the Bender book recommendation. I have not read everything yet. Yeah, and she is writing a new one as well. So if you guys are interested, this is a book by Emily Bender. Bender linguistics book. This one, Linguistic Fundamentals for Natural Language Processing. Somebody asked about getting started with linguistics if you have an NLP background. So a book that I enjoy, and Emily's great. She was one of my professors and mentors in grad school. Next Wednesday, I've had a lot of requests for the BERT paper, so we might get into it. Yeah, unless somebody else has something, super compelling. But I want to learn more about BERT, you guys. And I think it also builds on this paper. No, I don't just want to learn about BERT. I believe, yeah, it also depends on the Transformers paper. So I think it's a nice, logical extension of what we've been doing so far. Yeah, so that's my plan so far. And Henry says, yes, BERT. So unless I hear some objections in next week, I think that's what we'll be doing. So thank you so much for joining me. I will be back on Friday for live coding. Maybe we'll work on a transformer. Yeah, I think that would be fun, and I think I'm going to try and use Python this Friday because I've done a couple Fridays of R, and I know people get grumpy when I do too much R, even though it's a great language and I really like it. So pencil in on Friday at 4 Pacific, Transformers with Python, and I will see you then. Thanks so much for joining me, guys. Bye.